So Volker already went through this, but I have a slightly different take. What are symbolic links? And I'm sorry, you guys are the guinea pigs for this talk. I am planning to give it to less technical users in different conferences in the good tradition of code reuse. So I'm going to go through what file system objects are and how they're used. One of the things I realized in preparing for this talk is most computer users who grew up on iPhones and Android, they don't know what a file system is. Most iPhone and Android users, they only know applications. The applications store things, obviously, in a file system. We know that as file system engineers and users, but the users themselves don't. Every application is a separate silo that only looks at its own data. So most people really, these days, most young users don't actually know what a file or a directory is. There's a very interesting link there about how professors having new computer science students coming in are having to actually explain what file systems are and how they work. So users only just search. They search for an object by name. They don't know where it's stored. They don't really care. The result of this is whenever my family want to do anything, I have to help them move objects around, move their photos, link between applications, share things on WeChat, etc. So let's take a step back and say, what does a file system look like? This is the most beautiful picture as an abstraction I could think of. It's an upside down tree, the root at the top, the leaves of the files, the branches that and the nodes in the branches are the directories, of course. So what does this look like? And again, Volker's slides were probably somewhat better, but here's a typical Unix file system. Starts at / at the top. My stuff is in the home Jeremy, and under there I have demonstrated documents and music. I have one music file. People who know me know I probably have a little more than that, but there's Yo-Yo Ma, one of my favorites. And there can be spaces in the file names, etc. And then if you look to the left, you'll see the temp directory where applications store their temporary files. And then down here you have things like user bin and the ls binary, which on a terminal you would use to list the file system. User add, which is a privileged command to add users. The difference between privileged commands and why symlinks are dangerous will become apparent later on. But there's the key, the ovals are the directories, the squares are the files. So very simple. Things got a little more complicated. So how do we deal with this as application developers? Sorry, I can't see the next slide on my screen, so I'm just having to try and remember, and sometimes I forget what the next slide was. So if you think about the file system API, it was originally very, very simple, the Unix file system API. You had open, create, was a variant of open, unlink, make dir, remove dir, stat, and then the metadata operations, chmod, chown, and then you have change directory, etc. But paths were coming down from root or from the point of the current, there was an idea of a current working directory, which is where you actually are in the file system hierarchy right now, and paths are relative to that. So it's very simple. You can get to any file on the system, file or directory on the system by starting from root and giving an absolute path, or you can get relatively to anywhere else by using, and on this slide, the stat shows if the current directory is home German music, I can get to my Yo-Yo Ma MP3 file by just accessing the relative name. So the first interesting change was something called hard links. Now, hard links look on the surface similar to symlinks, but the difference is they're not dangerous. They're actually useful, quite easy to use. I think the genesis behind hard links was essentially to save disk space, which used to be very expensive. Nowadays, you can get, 8 terabyte drives from Costco for $100. So disk space is cheap, but that wasn't always the case. So here is an example of a hard link. the two commands on the screen are ln, which is the command you would give on the shell, and then there is the underlying C API, which is link, which actually creates a new name /temp/lls, which is another name for the same file, user bin ls. So as you can see, the red line there shows LLS becomes a new name to the same binary that you might invoke. They create a new directory entry name that points to the same file data and metadata as another directory entry. They cannot be made to directories. I believe there was a version of Unix where that was tried, but it led to disaster, loops, etc. So that was removed. And all they do is they create a new absolute path to the same file. And it allows you to access the same file through different paths, which can save data storage if you're accessing the same data. They appear to be created for the incompatible time-sharing system around 1969. So they're kind of old, they're harmless, but they show that the file system isn't necessarily a simple branching tree with leaves being the files at the end. Sometimes the branches can stick together, as it were. So now we get to the meat of the talk and the disaster. Symbolic links, and that's the same command on the command line ln-s. I would be willing to bet that most users don't really know the difference between hard links and symbolic links, otherwise called soft links. But symbolic links can be made to directories. An example of this is /home/foo, which in this case is a symbolic link to the directory sbin. Sbin is where the system binaries are kept, and that can be more dangerous. And here is another one under /home/jeremy/documents, somebody making a symbolic link of the name bar, which actually ends up pointing to the program user-add. So if you actually tried to invoke or access home Jeremy documents bar, you would end up accessing the file user-add, which might not be what you want. Interestingly enough, the reason for them, from what I've been able to discern, is that disks used to be expensive. Mounting a new disk pack on Unix was a rare event. You would get one once a year or so, and you might want to reconfigure your data storage, but not necessarily have to change the paths that applications use. So you would put a symbolic link in to allow an application to keep working with the same data, but go to a different disk type. So they allow the creation of a new object in the file system that causes the kernel, when it's walking the path, to point to any arbitrary target anywhere else on the file system. And that happens transparently to applications. This is the problem. They don't necessarily know that they're traversing a symlink. They just go somewhere else. And not only symlinks to files, which would have been bad enough, but you can symlink directories as well. So you can create loops. Home, Jeremy, documents could be a symbolic link to home, in which case when you try to traverse it, the kernel would sit there spinning. So the designers of this had to create a new error code, eLoop, meaning you've created a symbolic link loop, which to my mind probably should have been a warning that, this isn't a great design. It's convenient, it's easy, but once you start having to create new error codes, you should step back and think, am I really doing the right thing? Of course, they didn't. Interestingly enough, they first seem to have been created from Multics in 1965, which predates Unix. But the problem was they were added by the Berkeley Unix designers into 4.2 BSD. I'm going to quote from the slide about how they announced it. Symbolic links have been added to release 4.2 of Berkeley Unix. This feature frees the user of the constraints of the strict hierarchy. Why does this sound very much like Berkeley? That a tree structure imposes. And this flexibility is essential for good namespace management. Oh, really? Yeah. So what do symbolic links look like for people writing applications? Well, they look like a bear trap that's buried in the bushes or under the grass that you can easily step in, and it'll take your leg off and kill you. Why is this? So why are they so bad? Volker already demonstrated this beautifully in his diagrams, which is somewhat better than mine, but you're going to have to bear with me. They allow paths to change on the fly with no warning. So they create a whole class of time of check, time of use, top two, race condition security problems. And here's the killer. If Symlinks really made it easy to put a new disk pack in and keep applications running, they should have been an administrator-only option. They should have been root-only. They're not. They can be created anywhere at any time with anyone who has write access into a directory. This is a disaster, and I will demonstrate. They break the beautiful tree abstraction. It's no longer a tree, it's a graph. It has loops, it's a mess. And they also ended up completely shattering that beautiful API I showed you here. I mean, beauty's in the eye of the beholder, but that really is a very simple, easy to explain conceptual model of how you access files and directory. This is utterly useless now. Let me explain. So once you've got symlinks in your file system, sometimes you have to know about them. Well, you've got to operate in them somehow. So the first thing is, how do I find out if I'm accessing a symlink? So the first change was the addition of the lstat or link stat system call. So if you give a path to the original stat API, it would, and still does, silently, transparently follow symlinks in the kernel. You don't know you're following a symlink, you just get pointed at the target. Having lstat allows you to say, oh, is the last component of the path I'm passing you, is it a symlink? If it is, it will be reported in the structure that comes back. And as Volker already pointed out, it only detects a symlink in the last component of the path, the yo-yo-ma.mp3, if you look at my previous example, not in the home Jeremy music. Home, Jeremy, and music, all of those could be symlinks. lstat wouldn't know or tell you. So how is this easy to get wrong? And it really is easy to get wrong. lstat, here's a path. Dangerous path because it's been given to you by a completely untrusted source, users, you can't trust them. So you say, well, I don't want to follow this if it's a symlink. So you say, if it use lstat it, if it's not a link, then I'll do a dangerous operation on the dangerous path. And Volker demonstrated this somewhat better, but here's my explanation of the same problem. There's a race condition. After you've done the lstat, the race condition starts here. You check whether it's safe, and after the lstat, somebody can have moved the path out of the way, symlinked something else there, and what you're looking at no longer reflects the reality on the file system. So if the attacker can rename dangerous path and replace it with a symlink to somewhere you don't want to go before you call do dangerous operation, but after the lstat, then you apply your dangerous operation on the attacker's path, not where you thought you were. And obviously, as Volker explained, this is very hard to fix in Samba. So again, great minds think alike, or in this case, a great mind and a mediocre mind. We both did the search on Symlink at the CVE database. And I found 1,361 records, CVE records, for symlink races. And you might think, well, you know, these are too narrow for me to care about. Surely there can't be that many. Well, A, that's a lot of CVE problems with symlinks. And B, they're still happening. This isn't just old applications. These aren't just old CVE reports. There have been many symlink mitigation APIs, which I'm going to go through, that have been added to POSIX to try and fix this race condition problem. But the symlink races still keep occurring in the applications. And my feeling is that the APIs now are essentially impossible for application developers to use safely. They're just too many of them. They're too complex. People get it wrong, and they will always get it wrong because these APIs are essentially unusable for normal developers. And it's very similar to if you remember the Linux kernel mailing list, have ponies or whatever argument about how to do atomic file access and metadata, which required Ted Cho to explain how you rename a file safely and atomically, and etc. People don't know how to use these, unless you spend your life doing this. And even if you do, you can still get it wrong. They're too complex for safe use. They just are. So how, once the problem with symlink races was realized, rather than saying, well, let's remove symlinks, people started to add mitigations into the API. And this is the rabbit hole they went down, and now they're really stuck. So the first one was, as Volker has already pointed out, no-follow. So you add that to the open system call. Looks perfect. Hey, don't follow symlinks. But in practice, doesn't do what you expect. As Volker pointed out, it only prevents the last component in a path name, the yo-yo-ma.mp3, not the home Jeremy music, from being a symlink. It's like Elstat. Ignores symlinks in non-terminal components. So here's an example. Here you've got your database application running as root, checks that data MyDear is okay. You want to access data MyDear password. Here's your classic time of check. Now the time of use, the renames data MyDear to data out of the way. You symlink data MyDear to /e to the file for writes, even with no-follow. You are pointing to etc. password. Great. Not exactly what you intended to do. So here are other mitigations. So here's, Volker already demonstrated perfectly, but here's another explanation. What Samba has to do is we change directory into the parent directory of the file we want to access. We use real path to check it hasn't been symlink race. Then we use no-follow to open a handle on the file. Then we change directory back to where we should be. So that's what Samba does. Or we can use openat. And openat has the directory file descriptor as the first operation to this. Now, if that directory file descriptor uses no-follow in mode, in flag, sorry, you can ensure that you're opening the file that you wanted. But remember, the path that you pass to openat has to be sanitized and checked that there are no slash characters in it before you are safe from symlink races. So that means you can no longer, you must check that it's where you need to be, and you can't trust anything coming in from the user. And of course, as Volker's talk already pointed out, you've got a chicken and egg problem. How do you make sure that dirFD is where you need to be? You have to, at some point, you have to check that you are where you expect to be, because the handle on the parent directory also has to be protected against symlink races. And that's where you got into the using openat, walking down the path each way to avoid any symlinks. So because of this, it realized that open was not enough. You cannot create a new directory with open. You cannot remove a file. You cannot unlink a file or delete a directory with an open call. Arguably, you should. You should be able to use an open handle to do any metadata operation on a file, but that's not the way That's actually more like the Windows one. You get a handle on something, you can do an operation on it. So lots and lots of new system calls had to be added. You've got openat, makedir@, unlink@, link@, rename@. Every single one had an at variant. And some of them are slightly changed. Instead of access, you have faccess at, which looks like it takes a file descriptor, but it really doesn't, or gets complex. Fchown at, again, rather than chown. So you've duplicated all the system calls. All the original POSIX system calls you can no longer use safely. Who got the memo around that? Nobody. Just, oh, here's some new system calls you should use. With slightly different semantics. I think, to be honest, this is where the legacy Unixes, everything except AIX, is where we lost HPUX, True64, all the old Unixes. They simply couldn't keep up with the flurry of system calls that are needed to protect against symlink bases. They died. I mean, even Solaris, I'm not sure has all of the mitigations needed to be completely symlink set. So our original clean and beautiful POSIX Filesystem API doesn't look very clean and beautiful anymore. And of course, all these system calls have to work. fchmodat still doesn't work. The oh no follow flag in chmodat is documented in Linux as, oh, by the way, this doesn't work. We'll still follow symlinks. Good luck. So Pathnames. Pathnames as a concept are now utterly broken in POSIX, in Unix. If you have any application, it allows any untrusted input, or you try and use more than one component at a time, you can be symlink based. You have to split it off one component at a time and use the at functions. It's the only safe way. How many applications have you actually seen that do this correctly? And it gets worse. It's still not enough for a feature complete application. There's no get etc at or set etc at. You have to open the file and use the file descriptor. And so if you have to do an extended attribute operation on path names, you have to do the chdir real path, get or set etc, change dir back. You still have to do that. So, is there a question?
Yes, there's a question in the chat.
Can you read it me? Sorry.
I can, but I might butcher the name of a syscall. So, Tom Toppy asks if regarding Linux new FACCESSAT face set.
Tom, just speak up. Tom, just
speak up, Tom.
You.
I'm here. I didn't want to interrupt, but since
no. Please feel free.
Been done. Don't these at calls all take paths? So you mentioned this takes a file descriptor. What's an access to a file descriptor with at?
Exactly. The file descriptor they give, the first one is the directory, is the file descriptor on the directory. They also take a path. These ones like fchmodat and faccessat, you can actually give a null path and they will operate on the file descriptor.
Yuck.
Yes, okay. Exactly. Thank you, Tom. I'll be on.
Who architected that?
All right. Clean and beautiful. Yes, exactly.
And now Linux is no doubt stuck with these forever, so they're going to resist any suggested change, right?
Yep. We're only halfway down the rabbit hole too.
Oh my God! All right, please continue. I'll get my barf bag handy.
Yeah, it's worse than it looks, and as Bjorn mentioned yesterday, not only is Unix dead, it's starting to smell really bad. Funnily enough, he sent me a wonderful link to a piece by Rob Pike about the Plan 9 file system API, where he specifically calls out symlinks as a disaster. He doesn't call them out for symlink racist or security. He just says they turn the file system into a mess, which is the least of their problem. So there you go. Extended attributes need more. So, okay, I know, let's add another flag. So Linux added opath. Again, or leaving all the commercial Unixes scrambling to catch up. So opath is an interesting call. You can do an openat with opath because it allows you to take a handle on a file or directory that you can do nothing with except pass as a file descriptor to the XXXat style functions. So it means that you can't read or write any data, but they're very convenient. Sometimes you want to take a reference to a file and you want to modify. You've got the rights to modify the extended attributes on it, but you don't want to open it for read or write. So you would really love to use the opath. You've already got it. It's convenient. So this isn't allowed. Opath specifically prohibits reading or writing extended attributes. So this is one of the most beautiful hacks I've ever seen. It's so ugly, it makes you want to vomit, but it's amazing. Completely Linux specific. So you open at safely a file with opath, no follow. So great, you've got a handle that you can't do anything with except use as a reference. But the Android folks, or whoever it was who did this, the Red Hat folks, they thought, well, you know what? I'd really like to do extended attributes on this. I know. Let's turn it back into a path name that can't be symlinked race. So on Linux is the concept of proc self FD. Proc self FD is a pseudo file system that contains inside it files that are each file name is the number of the handle that you just opened. So if you print into a buffer proc self FD and then the number of the handle you just got back from opath, you can then pass it to getXAdder, setXAdder as a path, and it can't be symlink raised. This is just so ugly. It deserves a medal, but it works. Samba actually uses this.
But this could be used to just avoid any of these add-based calls on anything but open, essentially.
That's true. That's absolutely true.
We don't need these fchmod add or something anymore.
Exactly.
Remove them again.
But this is so totally Linux specific, the proc self thing. And the other thing was, it's very interesting if you look, and I did before we decided on our solution for XAdders, I actually did a lot of experiments around proc self, because if you look at proc self FD and you do an ls-l or a stat on it, it tells you it's a symlink. So I thought, oh God, is it really a symlink? Could it be raised? So what I did was I wrote some code that actually opens the file, holds the handle open, deleted the file while I had the handle open, and then created a new file in the file system with the same path. Because what I wanted to know was, I knew it would point, I knew the file descriptor would be open on the old file because that's how POSIX works. I wanted to see how proc self would represent if I did a path name operation on proc self FD number, I wanted to know where it would say the symlink was pointing to. Do you know what they do? This is again so horrible. It's amazing. They change the name of the pseudo symlink to be proc self FD, to be the file name with brackets deleted on the end. So I thought, okay, well, what if I create a symlink? What if I create a file called brackets deleted? It's actually safe. Took me a long time. Took me about a day or two of doing experiments. But the proc self FD is actually safe against symlinks, despite the fact that it looks like a pseudo symlink and it really isn't. So this is pure Linux only semantics. God help FreeBSD and any of the other Unixes that have to implement this, that have to implement something that looks like the same semantics. I think they just give up. But I mean, applications now depend on this. It's a horror. Sorry, I better hurry up.
So the horror is spreading, Jeremy. FreeBSD is on the way.
I know. So Symlinks turned this beautiful tree into, and I have to give credit to the ex-KCD author Randall Munroe. Has anyone ever seen the movie Primer? It's a great movie, very low budget. It's a time travel movie that doesn't use the words time or travel. But that's the timeline of the characters in Primer. By the way, if anyone has seen that movie and understands it, would you please offline explain it to me? Because I still don't get it. But yeah, it turns the beautiful tree into this horror, this utter monstrosity that can be raised or ruined at any point. So, I mean, my assertion in this talk is now that path names, just the concept of path names, are unusable on POSIX completely. For a non-trivial application, for a regular person writing code on POSIX, you will have symlink races in your code, just guaranteed. And it's not even just your own code. You have to use libraries. The libraries you depend on, are they symlink safe? I believe they're not, and I'm going to prove it. And here's the spoiler alert: security library code. This is a reported bug, by the way, just in case you fear that I'm releasing a CV early or something, because it's still not fixed, but it is a reported bug. So look at your directory hierarchy: foo, bar, bas, bibble. Directory is last one, bibble is a file. On Linux, you run the set file system ACL command with the -r recursive flag. And what the -m says, modify the ACL on that file, add a new user. That's what the U is for. The new user GDM, which is just my go-to user when I want a random user who can't do anything. GDM is the user who runs the screen, the standard logon screen. So start at file foo and recursively change the ACL to add GDM to each one of those objects. Now you do strace. I'm not doing it live like Wonka did, but you can see the output. Look at these get-atta and set-atta calls. They are not symlink safe. And you can reproduce this at any point by doing set facl -r on any of your Linux boxes. These calls, which are normally run by root to change access controls on a whole host of directories and files, can be symlink based. So if you ever know root's doing that, or you ask them to do it for you or something, and you've got write access, you can almost certainly symlink race and change what they're accessing without them knowing it. Because they don't walk the path using openat. They're just using the path name-based calls, which are inherently symlink unsafe. Interestingly enough, I tried the same thing with chown -r. The GNU utilities people, they do it right. They're more cautious. They open every single path using opath. Not using opath. They open every single path, and they use the handle-based operations instead. Here's example number 2, and again, I have reported this, and I've been assured that it really isn't as bad as it looks. So it's not really a security problem. I'm not sure. So Git, I reported it to Git maintainer, you know who I work with. So Git had a security problem, CVE 2022, the numbers up there. Here's part of the patch that was added for that security problem. So the added definition is path owned by current user. And it's hash defined into is path owned by current UID. And this was the new function that was added, is path owned by current UID. So you can see they do an lstat, and then they check. Is the UID equal to the current running user ID? Can anyone see anything wrong with this patch? Is there any check that path isn't a multi-component path? Oh dear. I'm pretty sure I could raise this because what's being checked there in lstat path isn't necessarily I can symlink race it to point to something else. So maybe I have a path that is known by me, and I can point it to something that is owned by me, and it passes this check. Now, Git doesn't take privileges, so it's probably safe. But again, this is just an example of how dangerous this is. And this is written by security engineers writing a fix for a CVE. And it still has a potential symlink race. And Volker already mentioned this, but it's such a great CV that I also referenced it. Here's the, it's basically the Rust standard library. Remember, Rust is the new hotness that's going to save us from all security holes. They even had symlink races in their standard library. Unfortunately, this function does not follow symbolic links and will simply remove the symbolic link itself. Unfortunately, that check was implemented incorrectly. What are the odds of that? Again, can't be used. So let's go back and say, how are we going to fix this? I've got 5 minutes left. So Windows. You don't normally hear this from me. Learn from Windows. Windows did it right. NTFS has reparse points, which are used to cover a multitude of sins and are also available on directories, which I think is a disaster, but there you go. They have application followed symlinks called reparse points. By default, unless you're running in something called developer mode, you can only create them as root. And that's just the fix. Essentially, if you wanted to go back and go in a time machine using Primer Time Machine in Berkeley and say, no, make it root only, that would have fixed most of these problems. Because no code is safe from root anyway. If root's racing you, what the hell? Root has a right to do whatever they want. Unfortunately, it's too late to do this now. It will break systemd, for instance. Starting a user service absolutely depends on the user being able to create symlinks to system files written by themselves. So that would just stop. And we all know how everyone loves systemd and can never be changed. So number 2. So again, let's add another system call the Linux way. openat 2. Volker already mentioned this. It has 3 possible flags. Resolve beneath, which means the file descriptor you give it, don't allow anything to get escape from that. Resolve in root, which is for containers, I think. Then resolve no symlinks, which will give you eloop if you ever run into a symlink. So see the man page for the details, but as Volker pointed out, there's no glibc wrapper. It only fixes the problem for open and openat calls. Every application would need to be rewritten, and they're not using the existing course correctly. What makes you think they're going to change to use this? It is promising for the future. I've already mentioned the problem with absolute paths, etc., but we can work around that. As Volker pointed out, we're almost certainly going to use them. So there was a long discussion that on Linux Weekly News, and there's some really smart people on that site. And Linux Weekly News user who I only know as Willie, because that's his subscriber name, said, hey, why don't you add a priority process control option that basically says, for this process and this process only, if you hit a symlink, return eloop. And that breaks all existing applications, yes, but it breaks them in the right way, because that way you can test, you can add that process control, you can then fix all your code paths that do path names to actually follow symlinks manually. If you really want to follow them, you can follow them like we have to do in Samba, which is read the link and follow it yourself. Again, this is just an idea. Nobody's actually planning on implementing this. This is a nice idea that I quite like it. Second possibility, Linux Weekly user Nix. And this is an interesting one, but less likely. Change the symlink semantics so that you only follow symlinks that you created yourself, that are owned by a UID that you're running under. It's subtle. It's a nice fix. It still breaks applications. Don't think it would break systemd though, which is nice. It's probably too confusing to implement. It doesn't fix the problem for Samba because we're often running under different UIDs and we have to follow or not follow symlinks depending. But again, no one's currently implementing this. But these are some creative ideas around the problem. I'm nearly finished. So Linux actually has an implemented option, mount option, called mount no sim follow. What I suggest is that you download a Linux kernel tree and do a git grep for no sim follow. it's implemented inside name.i.c, which is the name, path name to inode tree walker. It essentially says, if I had a symlink, return eloop. It's perfect. Does exactly what we need. I cannot figure out how to turn this on. It's not in the mount binary. It's not. It's like an option that lives in the Linux kernel, but there seems to be no way to get to it. If anyone knows how to get to it or wants to hack mount to turn this on, that would be great. It's mount option number hex 100256. At that point, you could basically say, hey, my application, I guarantee you, is safe if you run it on a file system with mounted no symfollow. So the great thing about this option is that you can still create symlinks. You can still read symlinks. So, I mean, Samba would still work, essentially, because we read and write our own symlinks. We store DFS names in there. But, so you can still read and write symlinks, but you never, ever follow them. Can't figure out how to make it work. But this I really like. I would love application vendors to say, you know, this symlink stuff is a mess. We can only guarantee your security if you run on mount no symfollow. Would love that. Of course, it has to be, we need to advocate for this more, I think. So short term.
So no symfollow returning eloop. That's kind of strange.
Not really. What it means is that if you pass a path name to any system call that would have traversed a symbolic link, it returns eloop. And at that point, you have to say, oh, let me go find where it was.
Well, yeah, but it's not quite the same thing as what eloop traditionally means, right? It's kind of
no, I know, but they're easy. That error message was a mistake anyway. So, hey, they don't want to add another error code. It basically turns symlinks into Windows shortcuts.
Yeah, exactly. You know, you follow this. I ain't following it for you.
Exactly.
Right.
Yeah. And it allows specific apps to say, if you're mounted on this, I'm opting out of symlinks. Just, yeah, let's ignore symlinks. Let's, you know, and I'm setting a 10-year timeline. Let's eliminate symlink races by 2032. I would love to do that. I think that's very ambitious. I think we'll still be running into them when the UNIX epoch clock runs out in, what is it, 2037 or something? But 2030. There are some signs of light on the horizon. It's not all grim. Nobody's going to rewrite the applications. Nobody's going to rewrite the libraries. Breaking things this way, at least so at that point, you have applications that you can run on a known secure file system, which I kind of like. And that's everything. So